So we've looked at a myriad of multiple integration techniques. We looked at partial fraction decomposition, trigonometric substitutions. We looked at just basic substitutions. We looked at integration by parts. We looked at integrating products of sines and cosines and other trigonometric functions. And we looked at trigonometric substitution. And so now often comes up the question of, well, how do I know which technique to use? Okay? How do I know that that integral should be integrated this way? And frankly, this kind of question is a question like, how do I get rich? Or how do I win this war? It's not that there isn't an answer to it. It's that someone cannot provide you with a formula to get there. Okay? Someone cannot give you a formulaic way to know which integral to use. But with experience, you could gain insight into what method is at least worth trying. And that's how it's done. Don't believe anyone who, tells you that they know automatically. Even if it's your professor, if someone is very talented in math, then it's likely not worth their time in the age of computer systems to be solving integrals left and right by hand rather than trying to prove theorems. So someone with mathematical talent is far more likely to be productive by studying theorems and trying to prove theorems than doing a bunch of integrals beyond Calc 2. That's the reality. But you should learn them, and you should at least have some basic insight or intuition to how to do these integrals. And that's what we'll discuss here, sort of the broad kind of method or approach, you could call it, rather than some formulaic prescription that'll give you a concrete answer. And if someone does give you a formulaic prescription, I am sure it will be easy to find an integral that will sort of contradict that flow chart. Okay? And so let's look at the basic integration strategies. So whenever you approach any integral, one idea is to just simply simplify and rewrite it. Okay? You take a look at this, you see that cosine there, you think, well, maybe u substitution would work because, there's a du, but then there's that plus one. Well, hey, why not just try to rewrite this integrand? So you could split up, the cosine squared is in the denominator. So you could split this up into two terms, 1 over cosine squared, and then you'll have sine x over cosine squared. Well, that sine x is tan x, and 1 over cosine is secant, and 1 over cosine squared is secant squared. Well, now you have this, and it's much easier to see the antiderivatives of those being secant and tan x, and so you could solve that problem much more easily just by rewriting rather than sort of getting lost in u substitution. Okay, so you rewrite and simplify the integrand, and it's not working out for you so much. Well, now it's a good idea to try substitution. Well, you take a look at this and you try u is equal to 4 minus x to the 6th. Well, du then is negative x to the 5th dx. And so that's not going to work. But check this out. You have an x squared here, and x to the 6th is x cubed raised squared, right? So you will get 2 times 3 is 6, so you could write it this way. Now, if you chose u is equal to x cubed, then du will have the x squared in it. And in fact, that's one way to do this, is to choose u is equal to x cubed, and so du is 3x squared. And now notice you could sweep up the x squared dx term into the 1/3 du. Okay, so you just swept up 1/3 the x squared dx into 1/3 du, and you're left with 4 minus u squared, and you know that the antiderivative of that is arc sine. And so a very clever u substitution there worked out. Okay, the first u substitution would have not worked out, but we got a little bit clever, and we noticed one would work out. And this is one of those things that I would not feel bad about if I didn't notice. Okay, it's just one of these that you try, and then you're likely to slip up the next time you see it, and you do it multiple times, and then you sort of build an intuition about it. So that's the sort of second thing that you could try, is just substitution. It's the basic form. Third, you sort of get deeper into the actual methods that we covered. So if rewriting didn't work and U substitution's going nowhere, well, we could then try to classify the integrand and recognize some patterns. So for example, if you had a product of functions, you can try integration by parts. And again, that worked where taking derivatives of a term would simplify it, and integrating a term is easy. And so you could do that. Sometimes you'll see a function that doesn't look like a product of functions, but in fact is, right? Natural log of x is the product between natural log of 1, and in fact the easiest way to integrate log x is to do an integration by parts. Okay, so you could sort of take the antiderivative of 1, and that's x, and then you want to move that derivative to the other side. You do so at a cost of a boundary term, the natural log of x, minus, and now we could switch over the derivative to the natural log of x, and we all know the derivative of natural log of x is 1 over x, which would cancel that factor, and you'll be left with a very simple integral to do. Okay, and so when you're dealing with products of functions, you can try integration by parts, and even if it doesn't seem that you can, well, sometimes you can, right? And again, I would not feel bad about not recognizing this, but now I've tried it and it works. We also could look at products of powers of sines and cosines. For example, cosine to the fifth, and we've reviewed this technique here. You just basically split off terms from the cosine or sine, and you have this cosine x dx. You're going to sweep that under the rug of a du, and so you would have to have u equal to sine x. Well, that's cosine to the fourth, but cosine squared is 1 minus sine squared, and so you get 1 minus u squared with this substitution, and you could integrate that after foiling out. We also looked at integrals with terms that look like this, okay, where a is some constant, and here trigonometric substitution was advantageous. So if you look at this, sort of the first thing you might try to do is use substitution with that term in there, but you'll get e to the power of a square root u there, okay, if you do that. And that there are ways to solve that, but you'll end up doing a integration by parts. Another method to do it is to try trigonometric substitution. Okay, we have 1 plus x squared term, and we could use x is equal to tan theta. That'll give us a 1 plus tan squared theta in the radical there, and x is equal to tan theta, and our dx then is secant squared d theta. And then now you do another u substitution, and you have u is equal to secant theta, and du is equal to secant theta tan theta. So you just combine a tan theta with a secant theta, and you're left with a secant theta, which is u, and you'll get this term, and you'll do an integration by parts for that one. Okay, so that's a way to use trigonometric substitution. You didn't have to do that, and we'll actually look at a way that if we do get a square root, what else we could do. So another thing that we discussed was rational functions, and there, a general strategy is to apply long division and then partial fraction. So if we have this integral right here, well, we could do long division, and we end up with 1 minus 1 over x plus 1. It's easy to integrate that term, and here it's easy to integrate that term there. Okay, in general, you'll end up with you'll end up with a rational function in proper form, and that's reduced, so no common factors, and with a degree of the numerator less than a degree of the denominator. And so you could use a more complicated partial fraction, but I wanted to emphasize here that even if it's not proper, you could get a polynomial and a remainder term that is proper. And in general, don't give up, right? Try, so we looked at all these different techniques, and so again, going right from the top, we'll try to rewrite and simplify We'll try some substitutions. We won't be successful maybe. And then we'll take a look at some general patterns, products between functions, product between powers of sines and cosines, terms that look like this, or rational functions. And ultimately, maybe we could try different methods, and we just are persistent until something works out. I mean, take a look at this integral right there. Okay? There, one way to solve this is to do u substitution. Okay, so you'll have u is equal to square root of x. But unlike we're used to, okay, we'll have the u up here, but how is our dx going to look like in this case? Our dx will be 2u du, okay? And so we'll end up with an additional u du, and we could solve that problem by integration by parts there, okay? But notice that if we did du and then we took the square root of this, you'll sort of get in a quagmire. You actually had to work backwards there and square the x and write x in terms of u to get a coherent way to write dx, okay? That doesn't kind of get you in a quagmire, okay? You also could get an integral like this, and there you could try to rationalize, right? So you'll multiply by the conjugate radical. So you have this 1 plus x and 1 minus x. And this is 1, right? Multiplying by 1 is also sometimes could get you out of really sticky situations if you express 1 in a way to simplify the integrand. And so here you'll end up with, you'll square this term on top, so that's nice. And here you'll get a 1 minus x squared square root of that. Okay? And you could now rewrite this term in two integrals, okay? And you'll be left here, you just remember that that's arc sine x, and this over here, you just apply u substitution, and you end up with that final. And again, I would not feel bad about struggling about these things. I mean, you just have to do a lot and a lot of integrals, and someone could always throw you an extra integral where it's not so obvious, and you have multiple methods to solve one, and there are many different methods. And the sort of moral of this story is you get a lot of practice to get a lot of intuition, focus on the big picture of what you're doing. So for example, in products and sines and cosines, the big picture was to really ultimately do a clever u substitution, okay? For integration by parts, the big idea here, is that taking the derivative of u will get you 1, but integrating eu will just give you eu again. And so that's a way to simplify the integrand, okay? And we also looked at integration by parts where the integral oscillated back, right? You ended up getting the same expression that you started with, and you just solved for the integral algebraically. And so that's yet another sort of a method in our toolbox, and we got experience with it. And again, with these things, it takes a lot of practice, and you never quite master it, right? You're always kind of learning, but you do build a general intuition, and don't feel bad if you don't recognize the form. Even seasoned integrators will get stuck somewhere, and in these days there are not a lot of seasoned integrators because they are, if they have some mathematical talent, likely using it to prove important theorems rather than do a bunch of integrals. And so it's something that you got to go through, a rite of passage in your learning, and you just do as much as you can until you build an intuition about this.